Hello Year 12. So in this screencast I'd like to look at would like to continue with the binomial distribution. And first up I just want to introduce you to some notation, and that is how we write how a random variable is distributed. So we're going to be looking at different distributions. We're looking at the moment at discrete probability distributions, and one of the types of discrete probability distributions we look at is the binomial, where you can have two possible outcomes. So we're looking at the situation where it's heads, tails, pass, fail, that sort of thing. Rain, not rain, etc. Okay, and our familiarity with binomial distributions and expansions from a previous part of the course is brought into this. So, okay, so what you're looking at now is a breakdown of how we would talk about a random variable being distributed in a binomial way. So it would be written like this. This is our capital X, which denotes the discrete random variable, sorry, the random variable. We are looking at discrete examples at the moment. This little squiggly thing here, that means it's distributed in a B for binomial way. So when we do Poisson, this will be a P, and when we look later at continuous random variables, that might be an N for a normal. So that's introducing that sort of notation. And then in the brackets are our parameters. So what do we need to know about this distribution? We need to know how many trials we're taking and what the probability of success is. Remember, we've got 3 boxes to check with binomial probability at the types of questions. There needs to be a fixed number of trials. There needs to be the probability of success needs to be static from one trial to the next, and the third is that there are only 2 possible outcomes. Now, if we wanted to expand this out, right, how would this look? Then we'd say, righto, well, if I wanted to have a look at my distribution, this is how it would look, right? So I'd be saying, okay, so the probability that there are no successes, there would be my P. If P is my probability of success, then that would be 0, and 1 minus P, which is my probability of a fail, would be all of them, and that would be 0 successes, right? So 0 successes there. Then I'd go, all right, probability of 1 success. Well, there's NC1 number of ways of coming up with that 1 success. It could be on the first, or it could be on the second, or it could be on the third, all the way up to the nth. P to the power of 1, 1 minus P to the power of n minus 1. And this would continue all the way up to n, where we've got all our attempts are successful, and so no failures, 1 minus P being our failures to the 0. And we can write this in a shorthand fashion using sigma, k equals 0 to n perhaps, nk, then we write here P to the power of k, and then 1 minus P to the power of n minus k. So that would be the general distribution of our binomial probability scenario. Okay, so right now I want to look at, so we looked at, in the last class, we looked at how to calculate a certain number of successes, or use our calculator. I want to look at a couple of different parameters today. I want to look at expected value and variance of a binomial variable. Okay, so our expected value and variance of a binomial variable. So in order to lead into this, let's have a look at, or let's recap what the discrete random variable expected value and variance calculations were. So expected value of our random variable was the sum of each of our individual random variables by its probability. So you call that a weighted probability sum. And our variance was the difference from the mean squared by that probability. Again, a weighted probability sum. So let's have a look at this little example here and do the calculations just to bring it back to life for you. So our expected value for this distribution would be 0 times 0.3 plus 1 by 0.4 plus 2 by 0.3. So that would be, so we're taking each of the possible scores and multiplying by its probability. This is a weighted sum. Gives us our expected value. So we're going to get 0 plus 0.4 plus 0.6, which equals 1. So our expected value is 1. Now that doesn't have to be one of the values. It could be, most often is actually, falls between. So it's a mean. It doesn't have to be one of our values. All right. So that's 1, and we're calling this, often referring to it as mu. So when you see mu, we're talking about the expected value. Okay, that's an equal sign there. Okay, so our expected value of x is 1. Now our variance, our var x. Okay, so how we calculate the var x is that we take each of our, there's a couple of ways of doing it. And what I'm going to do firstly, I'm going to do this beneath. We're going to just have a look at we're going to subtract from each of the scores. We're going to take each score and find its difference from the mean. So this is no different to when we did univariate statistical analysis. We took each score individually to find the variance and found its difference from the mean, and then squared it, and summed them up, and divided by how many scores there were. This is a very similar process, but we're using the same weighted probability sum. So to explain, right, so in the first instance, we're taking the sum of each score, the difference from each score to the mean, squaring it by the probability. So to go through each individually, x equals 0. So the first one is 0 minus 1. So the difference from the mean, we're squaring it and multiplying by the probability. Okay, 0 minus 1, squaring it, multiplying by the probability of 0. Okay. At plus 1 minus 1 by squaring it by the probability, which is 0.4, and then adding 2 minus 1, the difference of 2 from the mean 1, squaring it and multiplying by the mean. So what we get here is we get negative 1 squared, which is 1 times 0.3 is 0.3. This is 0 here, and this is 1 times 0.3. So our variance is equal to 0.6, and if we wanted the standard deviation, so the variance is in this format, so therefore our standard deviation would be just the square root of 0.6. Okay, so that's how we calculate expected value and variance for a discrete random variable. Now, the binomial variable is a discrete random variable, so we are going to use the same technique. I'm just going to show you, first of all, how this variance can be written in a different way, because that's going to be very useful for us. So, okay, and this was actually question 6, I think, from maybe 10b, where you were asked to write this in a different way. So I'm going to do that now by just expanding this out. So what I've got here is the sigma of, I'm just going to expand this out. So I get x squared minus 2 mu x plus mu squared by the probability of x. Okay, now if I now expand this out, so I get x squared by the probability of x minus sigma of 2 mu by x by the probability of x plus mu squared by the probability of x. Now mu squared is a constant, so there's no x involved, so the px is irrelevant here. So this simplifies to, I get x squared px. Now let's have a look closely at this. This 2 mu, that's a constant, so I can bring that out the front. And then I've just got the sum of my x px's and then mu squared. Now this value here, does that look familiar? That's just that's it there, that's mu. So I can rewrite this as x squared px. This is minus 2 mu times mu, so mu squared, plus mu squared. And so we get the alternative, the shortened version of our variance, which is x squared px minus mu squared. Now, because this is our expected value, I will most often see this as just my expected value of x squared minus my expected value of x all squared. Remember, mu is just my expected value of x, and this is ex squared. So this is perhaps a more usable format to find the variance. Now, if we use this, let's just check it on my calculations here, that var x, I could have written this another way. Perhaps I will do so just off to the right here. Now, how do I calculate? So I'm going to calculate it in this fashion. So I'm going to bring this down and do the calculation here. Okay, so what this does is my expected value of x squared. So I square each of my x's and then multiply by the probability. So that would be 0 squared by 0.3 plus 1 squared by 0.4 plus 2 squared by 0.3. And then we subtract the square of my expected value, which is 1 squared. So what we get there is 0 plus 1 squared by 0.4 plus 4 by 0.3, which is 1.2, subtract 1. So we get 1.6 minus 1, which is 0.6. So we get the same value there. Just perhaps a more user-friendly format right there. Okay, so now we're going to have a look at our binomial distribution and what the expected value and the variance of those will be. We get an interesting result because of binomial, a particular case, remember, of just a discrete probability distribution, but because of the nature of it, we've only got two possible outcomes, where the probability of success is p and the probability of failure is 1 minus p, and we've got n trials. Let's have a look at what happens. Okay, so let's give this the treatment. We're just looking initially just having one trial, right? We've just got one trial of a pass-fail situation. Now, x represents the number of successes. So the number of successes can either be 0 or 1. Now, the probability of success is p, so the probability of failure, no successes, is 1 minus p, and that's what we've got in our table here. So let's calculate the expected value of x, given this information. All right, well, let's go to work on that. Expected value of x, well, it's just going to be my weighted probability, 0 by 1 minus p plus 1 by p. So my expected value of x is just p. Okay. My variance of x, well, that's going to be my difference of each of my x's from p. So 0 minus p, square it, by 1 minus p. Plus, now I've got 1 minus p squared by p. So if I run that through, I'm going to get p squared by 1 minus p plus p by 1 minus p all squared. Taking out the common factor of p 1 minus p, I get p plus 1 minus p. Now the minus p and minus p cancel, we're just left with 1 here, so I'm just left with p 1 minus p. Need another line. Okay, so my expected value of x, p, my variance of x, my var x, p1 minus p. So now in n trials, my expected value of x is going to be, my expected value of x in n trials will be simply n times p, because I'm just going to roll this, same trial out n times. So my expected value of x will be np, my var x for n trials will just be np by 1 minus p, and these are my parameter values for my binomial distribution. Right, I've got 30 seconds on the clock. This is all quite intuitive, I think. Now, given this information, x is my random variable, distributed binomially, 6 trials, 0.4 probability of success. Then my expected value of x is just 6 times 0.4, which is equal to 2.4. My var x is 6 times 0.4 times 0.6, which equals 1.44. Here's our exercise. See you in the next one.